Hi, welcome to the screencast for 18.2. In 18.2, we start looking at the strengths of acids and bases. So I started out with the example here of which acid do you think would be stronger and why, and I've given you the choice of hydrobromic acid, HBr, or carbonic acid, H2CO3. And since H2CO3 has 2 hydrogen and HBr has just 1 hydrogen, it would seem reasonable that carbonic acid should be twice as strong. But it's not. Even though carbonic acid has 2 hydrogen, it doesn't give up either hydrogen easily in water. And HBr only has 1 hydrogen, but it does give it up easily in water. So strength doesn't depend on how many hydrogens are in the formula. It depends on how many hydrogens end up floating free in the water as hydrogen ions. So since HBr completely dissociates in water, it's called a strong acid, and we show it by using a single arrow to indicate that it has pretty much a complete reaction. It's really not reversible. HBr in water will almost completely break down to be Br minus and then H3O plus, or if you prefer, just H plus. On the other hand, H2CO3 partially dissociates in water, so it's called a weak acid, and it's shown with a double arrow to show that only some of the H2CO3 breaks down to give you HCO3 minus 1 and H3O plus. But a fair amount of the H2CO3, in fact more H2CO3 remains together than what breaks apart. So it doesn't matter how many hydrogen atoms are in an acid's formula. What matters is the strength of bond between the hydrogen and the nonmetal or polyatomic ion in the original acid. The weaker the bond, the stronger the acid. But the stronger the bond, the weaker the acid. And if you think about it, it makes sense because a weak bond means the hydrogen will easily get pulled off by the water, but a strong bond means the hydrogen will stay on the original acid. So what determines bond strength? Things like polarity, the intermolecular forces, the bond length, and the number of covalent bonds. It's kind of like breaking a stick. The length, the thickness, and the kind of wood all affect how much energy it'll take to break that piece of wood. So how do we compare strengths of acids and bases when we're in the lab? You can use something called a conductivity tester, where you put 2 probes down into the solution and you look and see how bright a light bulb lights up, or there might be several little colored lights and you see how many of those light up. A more quantitative way to do it is to use a pH meter, and you get an actual number where you can compare. So to sum up, strong acids completely dissociate or fall apart in water. That means the ionization equilibrium lies far to the right, and a single arrow is used to show it's a complete reaction. This also means that there's a lot of H3O plus free or H plus available in the solution. For a weak acid, only some of the hydrogen ions fall off or dissociate, so the equilibrium lies far to the left, and the double arrow is used to show it's reversible. Very little H3O plus will form, so only a little H plus is free or available in the solution. So just like in chapter 17 when we calculated equilibrium constants, or at least looked at equilibrium constants, we could do the same thing with weak acids. A weak acid can have an equilibrium constant calculated by comparing the concentration of the products to the concentration of the reactants. And instead of calling it KEQ, we call it Ka to signify it's the equilibrium constant of an acid. Since the product is hydrogen ion and then some anion, and the reactant is the amount of acid you started with, that's what you're really comparing, is how much free hydrogen ion is there compared to the original acid. So if you get a high number, if you get something bigger than 1, that would mean it's actually a strong acid because there's a lot of product being formed. So Ka values are actually always going to be less than 1 because there's always going to be more of the original acid left and less of the H plus being formed. And the smaller the Ka value, the weaker the acid is. And you can look up examples of Ka values on table 18.4 in your book. And in fact, strong acids aren't considered to have any reactant left, so you really can't calculate a Ka value for strong acids since your denominator would be a 0. So we just don't consider strong acids to have a Ka. So strength of bases is very similar to strength of acids. It depends on how much of the base breaks down or dissociates in water. That's going to depend on the strength of the bond. So again, the weaker the bond, the stronger the base, or the stronger the bond, the weaker the base. For a strong base, the ionization equilibrium will lie far to the right. And so, for example, NaOH completely dissociates in water. So we show that with just a single arrow. And I see I have a slight mistake here. The Cl minus here should be OH minus. That makes a big difference because that means there'll be a lot of OH minus free and available in the solution and very little H plus in comparison. So again, this should be OH minus right here. For a weak base, on the other hand, the equilibrium lies far to the left and the double arrow is used. So for example, methylamine, CH3NH2, only partially dissociates in water, so it's shown with the double arrow. So CH3NH2 actually takes a hydrogen from water and becomes CH3NH3 plus, leaving behind the OH minus, so there's very little OH minus being formed and available in the solution. Weak bases also form equilibrium mixtures of molecules and ions, so just like we can calculate an equilibrium constant or Ka for acids, we do the same thing for bases and call it Kb. And again, there's always going to be more reactant than product if it's a weak base. So you're really looking at how much smaller than 1 is the number. The smaller that number, the weaker the base or the less of it that falls apart. And those are the main ideas for 18.2.